Right. So we're going back to substitution and elimination. We left off talking about the rate law of SN2 or SN1, I'm sorry. And we talked about the different factors like the solvent. We didn't really talk about the nucleophile, but we're going to talk some about that today. We talked about the solvent. We talked about the transition state. What I didn't do was go through the energy diagram, but it's in this summary right here on that. I guess the second or third page. There's a summary of each reaction, right, or each mechanism. So the SN2 energy diagram looks like this, where it's just one hump because it's concerted, and you're going from reactants to products. And then for the SN1, you go from reactants to intermediate, and then intermediate to products. I guess I talked about it because I see it's highlighted. So, but I wanted to make sure we touched that. So now I want to look at these problems right here, and we're just going to go through and answer the questions. So first of all, so this is a substitution. We're not worried about the mechanism at the moment. Let's just figure out what the product is. What would the product look like for this reaction that's shown in reaction A? If I'm doing a substitution, what am I substituting and how does it happen? Not mechanistically, but anybody. Right, what would the product look like? If this is my substrate, this is my nucleophile. Keep in mind, sodium does not participate. It's a counter ion. But that's actually a salt. What's the product going to look like?
Sorry, I just joined. I'm going to say the OTS.
This is my leaving group. Right, it's always the most electronegative atom, or the most, how do I put this? A functional group that can be stabilized, right? So the tosylate I showed you on the chart the other day, it's actually a really good leaving group. This right here, right? This is the O, and then this is the TOS part, toluene sulfonate. So it's actually an excellent leaving group. So what happens in a substitution? We've been talking about this long enough now that even if you don't know the arrow pushing part or the guts, the details about the transition state and all that, you should at least know what's going to happen in a substitution reaction.
So that oxygen connected to the CH3 is going to replace the bond of the leaving group with the carbon.
Thank you. So in a substitution, your incoming nucleophile substitutes for the leaving group. I mean, that's the bare basic definition of substitution. Your leaving group gets replaced by a nucleophile. And then you're left, of course, with this, but we don't really care about this because it's trash. It goes in the waste. Na plus and then OTS minus. All right, what about the other reaction? Reaction B, what's that product look like? Again, you need to be able to identify the substrate. The substrate is going to contain my leaving group. And then cyanide is my nucleophile. So what is that product going to look like?
Can I ask, why is that charge? Is
On
it
carbon?
supposed? Yeah.
The cyanide molecule looks like this, right? So the carbon has 5 electrons around it, but it normally has a valence of 4. So when you calculate the formal charge, it's 4 minus 5, which is -1. Let me fix that.
Okay.
Yeah. So that carbon has a formal charge of -1, right? If, if we go back to part 1, when you want to calculate the formal charge, is always, there's 2 ways to think about it, but I always teach it the most basic way, which is valence, where look at the periodic table, look at the atomic number, get the valence electrons for carbon is 4, and then minus actual, which is what's around the carbon. So you got a lone pair here, that's 2, and then 1 from each bond, right? So that's 5 total.
Okay, well it's gonna create a new carbon-carbon bond.
Good. Here, right? Is that right?
Yes, and just to make sure. Okay, yeah, I see that, yes.
Right, and then that triflate leaving group is this. It'll normally end up with whatever the counter ion is on that cyanide. So if it's a sodium or potassium or whatever, that cation will normally end up with the leaving group and form a salt. But I don't have a cation depicted here, so we'll just leave it how it is. All right. So that's the hard part. So now let's go and answer the questions. We've already done A. All right, for B, it says, for reaction A, explain why the rate of reaction will not be affected when you increase the concentration of the nucleophile when the reaction is done in ethanol. That's a lot of words to unpack. Ethanol is, ethanol is what? As a solvent, protic or aprotic?
Isn't it protic? Ethanol doesn't
Yes,
have an OH.
It's protic, good. Right? What does that mean in terms of this substrate, which is allylic and is secondary? What do we know about secondary carbons as it relates to substitution? All right, let me throw some more sauce in there. We talked about 2 substitution mechanisms, SN2 and SN1. SN1, what's the preferred type of substrate for SN1? Well, let me even back up. What's the preferred solvent for SN1? Is it protic or aprotic?
Aprotic.
Well, SN1 is protic. For SN2, it's aprotic. So for SN1 reaction, protic solvents help speed it up. Remember, we talked about that here. If it's SN1 and you do it in a protic solvent, the solvent is going to solvate the leaving group and stabilize it. And that's going to increase the rate. Excuse me. So when we get down to here, let's read the question again. And this is a lot of, it's kind of a pitfall for any class. Like if you're taking the exam, if you read the question and you don't understand what it's asking, then it's hard to answer it. So it says for reaction A, explain why the rate, so it's asking us about the rate of reaction, whether it's going to be fast or slow, will not be affected. So it's not, the rate is not affected when you increase the concentration of the nucleophile when the reaction is done in ethanol. Ethanol is a giveaway, right? So if it's protic and we have a secondary substrate that can undergo remember that we talked about this, the secondary substrates can do SN2 or SN1, right? So what's going to be the determining factor is going to be the solvent. So if we're in a protic solvent and protic solvents favor SN1, how do we answer that question? Why does the rate not change if you start adding more nucleophile in? What do we know about the SN1 reaction or S1 mechanism as it relates to the nucleophile? In other words, what's the rate law? If you know the rate law for SN1, then you can answer that question.
Oh, right. The rate law is just the it's just the concentration of the electrophile.
Yes, yes. Or we'll call it the substrate, right? So if we take this, if it's a secondary, it can go either way. It can be secondary, can do SN1 or SN2. Right, but the solvent dictates that it goes through a SN1 pathway because protic solvents favor SN1 reactions. So if it's protic and we know what the rate is, how do we answer that question? I think you answered it already, but give it to me in a more succinct manner. Like, how do you answer the question?
So, knowing that ethanol is a protic solvent,
Okay.
generally adding a nucleophile to a reaction would obviously change the rate. But since this reaction is SN1,
Right.
and the rate of the reaction is not based off of the nucleophile, it is only based off of the substrate.
Excellent. That's exactly right. So since it's in ethanol, it's SN1 and independent. If I can spell, come on, Russell. Of nucleophile concentration. So if it's SN1, the rate is independent of nucleophile concentration. Good. Let's answer the next question. Question C. Explain why the rate decreases when the solvent is switched from DMSO to ethanol in reaction B. Reaction B, what type of substrate is that? Is it primary? Is it secondary? Is it tertiary?
Well, since it says the rate is affected, it must be SN2, and it could be tertiary. No.
It's primary,
Secondary.
right?
Primary.
Tertiary would have 3 groups attached to what a leaving group is. So this
Right.
is tertiary, this is secondary,
And primary.
and this is primary.
Okay.
Right, so it's a primary substrate, and that means that this can only do SN2 only. So what's the rate law for SN2? We know the substrate is there
The nucleophile.
and the nucleophile. We know that. All right. So the question is, when I switch from DMSO to ethanol, the rate decreases. What am I doing by switching from DMSO to ethanol? DMSO, let me move this up too. DMSO, is it protic or aprotic? We know ethanol is protic. We just said that up top. All right, so this is protic.
Well, it doesn't have an H to give, so isn't it aprotic?
It's aprotic. Right, and this favors SN2. Protic solvents slow down SN2. Right, so so now we can ask that question. Explain why the rate decreases when the solvent is switched from DMSO, which is aprotic, to ethanol. How does a protic solvent slow down an SN2 reaction? What happens?
Steric hindrance. No, doesn't it interfere? Because when you give an H proton, you interfere with the nucleophile.
Yes. So what's that process called? When the nucleophile gets surrounded or put into a cage, basically by the protons from the solvent.
I don't remember, but I know you've said it.
Let me go back. All right, it's solvation. That's what happens. Put a protic solvent around the nucleophile. It's going to donate protons to the nucleophile and cage it up, basically put it in a cage and slow down the reaction. So when we go to here, we can say that, right? The reason the rate decreases when the solvent is switched from aprotic to protic is due to solvation. All right, any questions about that? It's a lot of information, but if you have a question, you can ask it now.
Yeah, it is a lot of information. I was just thinking about that. So as far as, I guess this isn't really related, but as far as the exam, is it going to be like the last one where it's all online and then you have a few questions where you have to draw out the mechanisms?
Yes, it'll be just like the first test. Same,
Okay.
Same format. Some file submission, some matching, some multiple choice.
Okay.
Any questions about this, about what we've just done? All right, let's move on to another topic. We didn't do this. Let's finish this part and then we'll move on to another topic. So here, it's asking about that reaction that's up top. So I'm gonna go back and recap that. So we had these two substrates with different leaving groups. And we said that it was SN2 because the solvent was aprotic. The substrate was secondary, had good nucleophile, and you can see also here, you can see the inversion of stereochemistry. I don't think we talked about that yesterday, Wednesday. But we also see invert, that's common for SN2. All right, so knowing that, let's answer question 4. Right, if the concentration of sodium methyl sulfide is decreased by 10 times, and we already know what the rate is because we have the rate law up here. What happens to the rate of the reaction shown above? So reaction 1. If I decrease the amount of nucleophile by 10, right? This is my nucleophile. Right? We see that up top. We know that that's the nucleophile. If I decrease that concentration by 10, what happens to the rate?
It's gonna be H.
The rate should decrease by 10. Anybody not following that? If I'm take numbers and put them in here. So this is 1 and this is 1 over 10. Then the rate should decrease by 10. That's how that works. And if you're ever confused about that, just put the numbers in brackets. If you double both or if you triple both or so on and so forth, just put it in there and multiply them together. All right, let's do the next one. Questions about that? All right, so number 5 asks, it says reaction of R2-methyl-3-bromobutyl-benzene with sodium methoxide gives 2 products. That's a giveaway. If it was, depending on the mechanism, you either gonna get, if you watch that ICE method video, it talked about how you can distinguish between SN2 and SN1 based on the product stereochemistry. Right, so we're going to talk about that in a second. So it says choose the best representation of the transition state from the list below. Before we can pick the transition state, what do we need to know?
Sorry, maybe the first, primary, tertiary, secondary, and then also if it's SN1 or SN2.
We need to know the mechanism. Is it right? So is it SN1 or SN2? So let's go through the ICE method. That is identify, characterize, and execute. All right, this is a foolproof way of figuring out whether something is SN1 or SN2 or E1 or E2. We're not gonna do elimination. We're gonna start that on Monday, and that'll be on test 3. Right, so we have substrate. When we identify the substrate, what we're looking for is it primary, is it secondary, is it tertiary? So our substrate is secondary. Right, this is our leaving group. Actually, a very good leaving group. This is my nucleophile. This is Na plus, and then OET minus. Right, so salt. Don't let the counter ions throw you off. The sodium will not participate in a nucleophilic substitution. It's just there to stabilize the negative charge on the nucleophile. And then we're doing this in ethanol. What type of solvent is that? We got 19 people logged in and one person answering all the questions.
Prodic.
Go ahead, it's Prodic, good. What does that tell me? What do we know about Prodic solvents? And either substitution or SN1 or SN2, which one of those mechanisms is going to favor or be favored in Prodic solvents?
SN2. No, SN1, sorry.
SN1, good. Another giveaway for SN1 is here, right? If you notice in the product, you got 2 products. You got both stereoisomers, R and S, in the same amount. So this is racemization, right? You started out with the, let's see if we can figure that out right quick. That's 1, that's 2, that's 3. That's S. And so over here you have R and S. All right, so you got racemized products. This is a dead giveaway for SN1. I'm not saying indicative, I say characteristic. All right. So all of that to get to answer the question, which transition state matches? Which ones can we rule out? And why? What is okay, let me walk you through that part. Is transition state 1, does that resemble a SN1 transition state? Because we know it's SN1. Or does that resemble another type of transition state? What's the rate law for SN1?
I'm sorry, it's K times substrate.
Thank you. I was about to start playing Jeopardy music. K times the substrate. Good. That means what? What about the nucleophile? Is it involved in the rate determining step based on that rate law?
No.
It's not. So when we look at transition state 1, this is the nucleophile, this is the substrate, and they're together. Does that make sense if we say that it's SN1?
Oh, so you would basically pick one that doesn't have the nucleophile in it.
Yes, because this is an SN2 type transition state. SN1, again, and I think it's making those logical connections is going to take time, but if we know the rate law and we know the nucleophile is not involved and we know what the rate determining step is, which we do, it's the loss of leaving group, and the nucleophile doesn't participate in that, it can't be TS1 or TS2. It can't be either one because both of those have a nucleophile involved in the loss of the leaving group. And we know that for the SN1, that's not the case. Right? Does that make sense? When we talked about the SN1, we said that the leaving group leaves first and then the nucleophile comes in, but the leaving group leaving is the rate determining step. So that means that the nucleophile has an absolute, and we just answered the question about that up top. The nucleophile has nothing to do with the rate. So it's not involved in the transition state for the rate determining step, which is loss of leaving group. So it's gonna have to be one of these two. Right, so the nucleophile is not involved in the rate determining step. So that means it's not involved in the transition state for the rate determining step. So it's got to be 3 or 4. Which one is it? And tell me if you, whichever one you pick, tell me why.
I was gonna say 3, just because bromine is usually partially negative.
Yeah, not usually.
It
Always.
is, yeah.
Yeah, it's always partially negative if it's attached to a carbon and the bond is breaking, right? between the carbon and itself. It's always partially. So you're right. So this is the correct transition state over here. This is incorrect because of the charge on bromine. Remember, when we talked about SN1, let me scroll back up. We said that in the transition state, where is it here? I don't think I showed it. I think we showed it over here. In the transition state for SN1, the bond that's breaking between the substrate, the carbon in the substrate and the leaving group, this is what it looks like, where the carbon that contain the leaving group is partially positive, and the carbon and the leaving group itself is partially negative. All right. All right, let's go to, that's a good question, actually. We're gonna skip over the eliminations. Let's go and let's do 741, and then we're gonna do 742 and 743. Let's see what we made of today. We got 13 minutes left. We can do it. All right, so for each pair, identify the compound which will react more rapidly in an SN1 reaction. So it's telling you that it's SN1. What does that mean to you? Protic solvents.
And I think primary substrates.
Secondary and tertiary substrates. Good.
Oh, okay.
We're good
Sorry.
though. Substrates. And good leaving groups. Those are the things that favor SN1, right? If it's a secondary substrate and a protic solvent, it's SN1. If it's a secondary substrate and an aprotic solvent, it's SN2. But all of these are said to be SN1. So let's go through them and see which one is fast, says which one is faster. Right. So let's look at A. We're going to do all of them. A is this is tertiary. This is primary, and they have the same leaving group. Which one do you think is faster?
The tertiary.
Tertiary. Why? You're right. There's a reason, and we talked about it. What is the first step in the SN1 mechanism? Because it's stepwise. Is it loss of leaving group or is it nucleophilic attack? The first step in the SN1.
The attack.
The first step is the loss of leaving group to give you a carbocation. That's what this question is asking about, which is basically asking which carbocation would be more stable if the leaving group left. Right, so the loss of leaving group is going to result in a carbocation. That's why tertiary substrates are favored, or allylic substrates or benzylic substrates, because they can be stabilized. Tertiary substrates are stabilized because of the methyl groups attached. Allylic and benzylic stabilized through resonance. So that's what this question is really asking. Which carbocation would be the most stable when the leaving group leaves? All right, so it's going to be for A, it's this one, it's tertiary. Let's look at B. It's the same type of problem. This is the carbon where my leaving group is. When that leaving group leaves and that carbon becomes positive, the question is which one of those is going to be a more stable carbocation? Because the leaving group is the same in both cases. So there's no advantage to the leaving group. What do you think? Is this primary, secondary, or tertiary right here?
Okay, so that's primary, so it should be SN2.
Yeah, exactly. And this is tertiary. So again, the same as the previous example. Which one is faster? Which one is going to give you the most stable carbocation intermediate? That's what it's asking.
Okay, so that would be the tertiary.
Yes, it will be this one. All right. What about here? Same leaving group. This one is allylic. All right. And let me give you some room to write. I'll just put it over here. If I have an allylic cation, versus just a regular alkyl secondary cation, what can the allylic cation do that the other one can't?
It has resonance structures.
It can do resonance. Excellent. So I can push this pair of electrons here. And put that plus charge there and delocalize it. Over here, I cannot do resonance. Right, so when I'm comparing those two, that's what I'm looking at. Because again, if it's SN1, chlorine is going to leave at some point, and you're left with a carbocation intermediate. So this is faster because it's stabilized by resonance. It's not, the cation is. Right, stabilized by resonance. All right, let's look at D. I'm gonna be quiet on this one. What are we comparing? Because the two substrates are identical with the exception of what?
The leaving groups.
Leaving groups. How do you know which one is better? What's the method for determining the quality of a leaving group? What do we look at?
Electro.
What can we look at?
The size, electronegativity, and
Mhm. Which is all of that is encapsulated in one number, which is what?
it's
pKa.
The pKa of the conjugate acid. Good. So all we need to do is go to our chart and see what the pKa for HCl is. Right, we see that chlorine is here. Has a pKa, the conjugate acid has a pKa of -7. And then the other one was the tosylate, which is -0.6. So let's go back down here and put those numbers in. Chlorine, where are you at? Come here. Here we're comparing leaving groups. So the pKa for HCl, which is the conjugate acid of that, we said -7, and this pKa should be lowercase p, is -0.6. Which one is a better acid? Which one has the, that looks so goofy, hops? Which one has the lowest pKa? That's how we determine what the better acid is. The lower the pKa, the better the acid.
that's gonna be. I can't see what that says. Why does it just say to the -7 on the left?
Yeah, that's the pKa of
Oh,
the
-7.
conjugate acid.
Okay, so that's gonna be the chlorine.
The chlorine
leaving-
has a lower pK. The HCl has a lower pKa. That means that chlorine is a better leaving group, right? And so that means that the first step is the loss of leaving group. The better the leaving group is, the faster it leaves. So this is going to be the fastest because of chlorine being a better leaving group. This is so jumbled up. So chlorine is a better leaving group. So this is faster. Right, in an SN1 reaction. So again, with the substrate, the only two things that you can compare in two different substrates would be the leaving group and the substrate structure. So if it's tertiary, secondary, primary, allylic, benzylic, so on and so forth. So you can compare those things and you can compare the leaving groups, right, to determine the rate, right? If it's a good leaving group, the rate is going to be increased. If it's a bad leaving group, I said this Wednesday, the rate is going to be decreased. If it's a tertiary substrate, it's going to be favored to go through SN1. If it's primary, it's going to be favored to go through SN2. If it's secondary, it can go either way, depending on the solvent. All right. Any questions about that example? All right, let's do 742. We got 3 minutes. It says consider the following reaction. So you have this brominated substrate. You react it with sodium cyanide and DMSO, and you get this product where the cyanide has substituted for bromine. All right. The question is, before we can answer any A and B, we need to know what mechanism this went through. So how do we determine that? Right, we can use that ICE method, identify, characterize, and execute. We can see that this is a secondary substrate. It's got a good leaving group. Right, it's done in an aprotic solvent. My suggestion is to look over that list of solvents so you can get familiar with what's protic and what's aprotic. And you got a pretty good nucleophile, right? And you have inversion of stereochemistry. What do you think? SN1 or SN2? We know it's a substitution because the leaving group got swapped out with the nucleophile. So it's not an elimination, right? Now, the question is, what mechanism did the reaction go through? SN1 or SN2?
2.
SN2, good. Now we can answer these questions. It says, how would the rate be affected if the concentration of the alkyl halide, which is the substrate, is doubled? So the rate is what? What's the rate law for SN2?
Substrate times nucleophile.
Good. So if I change any one of those concentrations, it's going to change the rate. So as now, how would the rate be affected if the concentration was doubled? Of the substrate.
It would be double the amount.
Yeah, the rate would double. This is a product. And so if I double one and keep one constant, if I multiply those two together, that means that the rate is going to be doubled, right? When you calculating the rate, it's always the concentration of whatever one of your reactants are. If it's second order, then you're gonna have 2 reactants. If it's first order, you got 1 reactant. If it's third order, you'll have either 3 reactants, or you can have an exponential increase or exponential rate, because one is the exponent outside of the bracket. One could be 2 and one could be 1, so on and so forth. Right, but this is second order overall. So that means that both of those exponents are 1. And that means if I double 1 and leave the other one the same, the rate should double. But you can't answer those questions unless you know what the mechanism is. And if you know the mechanism, then you know the rate law. What about B? How would the rate be affected if the concentration of sodium cyanide was double? That's the nucleophile. That's what it's asking.
I was gonna say, assuming the substrate is not changed, it would double also.
Yeah, that's right. And you can make that assumption because unless it's indicated, then you can assume that the substrate that doesn't change. So that's going to be 1 relative to the other concentration. All right, we got to stop here with 2 minutes over. We're going to do on Monday, we're going to do 740, not 744. We're going to start here on Monday. And then we'll warm up with 750. That shouldn't take us long because it's just drawing the products. And then we're going to talk about solvent effects on the nucleophile, and then we're going to move to elimination. So we'll start that on Monday. The test will be posted in about 30 minutes, and you can take it. It's start, stop. It's not timed, so you got until Sunday to submit it. Make sure that all of your file submissions are PDF documents, not JPEG, not TIFF, not GIF, not PNG, or the one I hate the most, HEIC. Please don't upload that, because I can't open it, and then that means I gotta leave you a note, wait for you to email me, and then wait for you to send me the questions, and then go back in and regrade the test. So PDF only. If you don't have a scanning app, I think Cam Scanner works great. There are other